Let me tell you something about dipole. See, a current carrying wire will behave like a dipole. Suppose you take a current carrying wire which is in the form of a circle, then you can write the dipole moment associated with that wire as NIA, where N is the number of turns that you have made out of that wire, I is the current in the wire, and A will be the area of that wire. So, now if you take a circular wire carrying a current of I amperes and you take only one turn, then the dipole moment of that particular wire will be I into pi r square. I is the current and I have taken the area to be pi r square. Let us read the problem and see how does this explanation of a dipole moment help us here. In hydrogen atom, electron moves around the proton with a speed of 2 into 10 to the power of 6 meters per second. Radius is 5 into 10 to the power of minus 11 meters. What is the equivalent dipole moment? See, here he has not given you any current. He has just told you that an electron, being a charged particle, is simply going around the proton, and that certainly constitutes the current. So, first write the current associated with this electron going around the proton in a circular orbit, and then use the formula NIA to write the dipole moment associated with this situation. So, let me first write the current associated with that electron, which will be charge divided by the time that the electron will take to go around once. Okay. So, here the current I would be, charge is Q, which you can write it as say E, electron charge, divided by time that it takes to go around once. That can be written as E divided by 2 pi r by V. So, EV divided by 2 pi r, where 2 pi r is the circumference of the circular orbit and V is the speed with which the electron is going round. So, 2 pi r by V would give you the time it has taken to go round once. So, EV divided by 2 pi r will constitute the current, and therefore, the magnetic moment mu is given by N. I have taken the number of turns to be 1 there. So, I will be EV divided by 2 pi r into A would be pi r square. So, that makes it pi getting cancelled, 1 r also gets cancelled. So, it will be EVR divided by 2, that is it, EVR divided by 2. Now, if you substitute the values, you get the magnetic moment. So, E can be substituted as 1.6 into 10 to the power of minus 19, that is the electron charge. Velocity is given to be 2 into 10 to the power of 6 meters per second. The radius is given to be 5 into 10 to the power of minus 11 divided by 2. Fine. So, that makes it 5 2s are 10. So, 10 into 10 raised to 6 would be 10 raised to 7. 10 raised to 7 into 10 to the power of minus 11 would be 10 raised to minus 4. 10 raised to minus 4 into 10 raised to minus 19 would be 10 raised to minus 23, and this will be 0.8 into 10 to the power of minus 23, which will be equal to 8 into 10 to the power of minus 24, and therefore, the correct answer is C option. In this problem, he wants you to compare the dipole moments. In the earlier problem, I think I had explained you about how a current carrying conductor can also behave like a dipole moment. So, let us read and understand. Two circular current carrying coils of radii 3 centimeter and 6 centimeter are each equivalent to a dipole moment mu. The currents in them are in the ratio. So, he says there are two circular coils of different radii, but still they have got the same magnetic moment associated with them. So, he wants you to compare the currents in them, right, to have the same magnetic moment. So, let me write the magnetic moments due to both of them and then equate them and compare the currents. So, here mu is equal to, as I had earlier said, NIA, but I am taking the number of turns to be 1, therefore, it would be only I1 into pi R1 square equal to I2 into pi R2 square. I have taken the currents to be I1 and I2 and the radii to be R1 and R2. So, that gives you I1 by I2 equal to R2 by R1 whole square. fine, and R2 is given to be 6, R1 is given to be 3. So, 6 by 3 whole square will make it 4. Therefore, the ratio is 4:1 and the correct option is D. See, let us read the problem. An electron of charge E moves in a circular orbit of radius r around a nucleus. The magnetic field due to this orbital motion is B at the nucleus. The angular velocity omega of the electron is. So, earlier I had told you that whenever you take a current in the form of a circular coil, there is a magnetic field produced at the center of the circular coil, and that is given by mu naught I divided by 2R. Fine. So, here he has not directly given you the current, instead he says there is an electron which is going around the nucleus, but electron being a charged particle, a charge continuously going round in a circular orbit would constitute the current, because current is basically the rate of flow of charge. So, let me first write the current which the electron going around the nucleus will constitute, and then write the magnetic field produced at the center, that is at the point where the nucleus is present, to be B, and then find out the angular velocity. So, just see the manipulation. So, now I will write the magnetic field produced as mu naught divided by 2R first. Now, I will replace this I by the orbital motion of the electron, and that will be mu naught by 2R, and I can be written as charge divided by time, and time can be written as 2 pi by omega. So, that makes it mu naught E omega, see omega goes to the numerator, divided by 4 pi R, mu naught E omega divided by 4 pi R. So, this is B. Now, if you want omega, omega would be 4 pi R B divided by mu naught into E. So, that would be the angular velocity with which the electron is going round, and that makes our C option perfectly correct. So, C is the right option. Let me tell you something about a solenoid. See, it is something like a spring made up of a wire, a conducting wire of course, and if you allow current to pass through that particular solenoid, there will be a magnetic field which is going to be produced by the solenoid. Now, if you imagine that the length of the solenoid is very, very large as compared to the radius of the solenoid, I am not talking about the radius of the wire that you have used to form the solenoid, I am talking about the radius of the solenoid. Say if this is the solenoid, this is the radius from the axis to the solenoid, right. So, if you take such a long solenoid, you can imagine the magnetic field produced by such a solenoid to be only along the axis, purely along the axis and uniform, and that magnetic field will be mu naught N I. The direction of this magnetic field will be purely along the axis of the solenoid. Fine? Okay. So, with that background again, and with of course, the rest of the knowledge which I had earlier shared with you about two parallel wires experiencing a force, because there will be a magnetic field produced due to one of the wires, and there will be another current carrying wire which is placed in the magnetic field produced by the first one. Therefore, naturally they are going to experience the force, and in our earlier example we had even written the force also. Let us read the problem. Choose the correct statement. No force is experienced, first option, if two parallel wires carry currents in the same direction. If two parallel wires carry currents in the opposite direction, a positive charge is projected between the pole pieces, say magnetic pole pieces, and a positive charge is projected along the axis of a solenoid carrying the current. Okay. Now, let us go in detail about all those options. If you look at the first option, as I just now said, there are two parallel wires, and naturally they will experience the force, because one of the wires is carrying a current that will produce a magnetic field, in the field of which there will be a second wire carrying a current, and it will experience a force. Fine. So, whether the currents are in the same direction or in the opposite direction as per the first two options, there will be definitely a force experienced between the two. Okay. Third, a positive charge is projected between the pole pieces. See, when there are pole pieces, magnetic pole pieces, there will be a magnetic field, and if you project a charged particle in the magnetic field at right angles to the field, definitely it will experience a force given by QV cross B. Of course, he has not told you how has he projected the charged particle, but if he says between the pole pieces, we can always imagine at right angles to the field between the pole pieces. So, we will discard even the third option also. Lastly, he says a positive charge is projected along the axis of a solenoid carrying the current. Just now I had told you that if you take a long solenoid, the magnetic field produced by the current carrying solenoid will be purely along the axis. So, if you project a charged particle along the axis, the direction between the velocity and the field would be either 0 or 180 degree, which makes the force experienced equal to 0, because sine of 180 is also 0, sine of 0 is also 0, and I am referring to QV cross P. Therefore, the fourth option is perfectly correct.